explain about this. So I just choose one of the today's seminar, which is Hilbert polynomials. And I think if you read our poster earlier, maybe weeks earlier, we put today's topic is maps between projective variety, but unfortunately, the last few lectures they did not mention anything about maps between varieties. So I choose a new topic to talk because I don't think we know anything about maps. Okay. And actually, I will start this lecture with a question. Does anyone remember how do we define graded idea last seminar? I think Adrian can help us answer this question because he is just the speaker, right? I think he definitely remember. Yeah, okay. 应该叫人创作啊。Writing an iPad, please. How do you define graded idea last session?
你的笔在哪里？
This is very torture.
What?
Yeah, we defined this last week, but actually in last section, we only defined this in a polynomial. Sure. Okay. Where is the eraser? All right. Last section we only defined this in polynomial ring, which is kx0 to xn. We only defined the graded idea in this ring, but actually we can generalize it to some other rings. We call this kind of ring graded ring. And first, let's see a definition, which is graded ring. The definition of a graded, first, let's see what is a direct sum. Okay, this is called a direct sum. And we define this, first we have two U1 and U2. And actually this thing should be subspace, but let's just ignore this because we can first talk about this in a ring. And we see that U is U1 and U2's direct sum if it satisfies two conditions. First, U is equal to U1 plus U2. That means that it is U1 plus U2 such that U1 is belongs to U1 and U2 is belongs to U2. And our second condition is that we need to satisfy for all U in U, it can be returned uniquely as U1 plus U2, and this should be unique. And actually, we can also write this as an equivalent definition, but I think I won't go how to prove the equivalence between here. It is if U0 is equals to U1 plus U2 with U1 in U1 and U2 in U2. Then there is only one condition, which is U1 equals to U2 equals to 0. Okay, actually, this is a definition of direct sum, and we will define our graded ring with this direct sum. And before that, let's see an example of what direct sum is. Let's consider U1 as R in R adjoint X, and our U2 will be monomials with degree 1 in Rx. Oh, I think it's this R. Then we can see that by our definition, U1 and U2's direct sum will be X plus B, right? Where A and B will belong to this ring R. And this is the direct sum, and we will define the graded ring with this thing. A graded ring is a pair S and SD, where D belongs to natural numbers, such that each SD is an additive subgroup. Additive subgroup, yeah. Such that the first thing is that S is equal to the direct sum of these SDs. And our second condition is that SD times SE will lives in SD plus E. And this is will work for all D and E in N. And there is a little remark that we say that SD are additive subgroups, so it will satisfy that 0 lives in every D, SD. Okay, and after we define this, we can see what is a graded ideal. Remember what we defined the graded ideal in our last seminar, which is if F is living in this ideal A, that we can imply every homogeneous component is lives in A. We call this idea graded idea or homogeneous idea. And we can see that this FD, we can not only define this in a polynomial ring, but in every graded ring, because we see that S is equals to this, right? So everything in S can be returned as sum of elements that each element lives in graded in this, lives in one SD. So our graded idea should be this, like this. And there is a proposition that says an idea A in S, where A is our idea, is graded. Sorry. Is graded if and only if this A is equals to a direct sum of A intersection SD. And I think this proof is just technically by definition, but let's see this, okay? Because if we skip every proof, this lecture will be nothing. Okay, and first let's see one direction. I think this direction is more obvious, quite obvious, because we see that if A is lives, if A is equals to this direct sum, then for all then for all U in A, we know that by the definition of the graded ring, since U is an element in this ring, we can write U as this thing, right? And since A is equal to this thing, and by the definition of a direct sum, this UI will lives in the intersection A intersect SD, right? And we see that this is a subset of A. So we prove that all UI lives in A, which means that all of its homogeneous components lives in this idea. And by our definition, this is a graded idea. And we can see other direction. We suppose that A is graded. And then also let's consider U in A. And again, we can write this U as sum of this UI, where UI are elements in SI, right? And we want to show that this UI lives in the idea. Oh, sorry. We want to show this actually because we already say that the idea is graded. And of course, UI lives in SI, and because we suppose that this idea is graded, we see that this UI also lives in A, right? Ui lives in A since A is graded. So because of this, we can see that this Ui lives in A intersection S. So we can write everything in this idea as direct as sum of elements, and this element lives in this intersection. And so because of this, we can conclude this the idea A, we can write it as a direct sum, right? Direct sum of A intersect SD. Okay, that is definition of graded ring, and we see what is a graded idea is. And I think we can go to an example of a graded ring. We consider K is a field. Then we can see that K joint X0 to X, and this is a graded ring, right? And every piece of this K, X0 to X and D is just spanned by the monomials with the total degree D. It's just the homogeneous polynomial in this ring, right? And you can see that according to this this example, we can see our last section's graded definition is just to follow what we define now, because that every component lives in a grad, right? And also, I think we can introduce another definition, which we will use later. It's called a graded module. And I think all of you learn abstract algebra 1, right? I think in our last class, which is a sneak peek, we talk about what a module is, right? And actually, we can just treat a ring as a module because you see, we just see R is a ring. We can just treat it as a R module R, right? I just think all of you know this one. What's simple? R module R, actually, do you learn linear algebra? Okay, so you learn what vector space is, right? So do you remember all 10 axioms of vector space? who taught you linear algebra? Ask me, right? Ask me. Okay, then if it has asked me, maybe.
He's one of the teachers in discrete math or what?
I think so, but he taught mathematics class of linear algebra for many semester, right? And I think Ali will told you what is 10 axioms of a vector space, right? Okay, so vector space, I think you learned that the scalar multiplication, the scalar will live in R, right? Where R is real numbers. If we change R into K, we actually can change this R into K, where K is any field, right? Because real number is just a field. We can call this thing a K vector space. And if we change this K, we do not allow this to be a ring, to be a field. It can be any other ring, then it becomes a module. We can see that this, maybe if we write as R module M, then M is a group with one LOC, which is addition. Yeah, and we can define a scalar multiplication. Actually, this is a group action, but I don't think you learn group action. Okay, the difference between ring and fields is that we ask every non-zero element in a field to be multiplicative invertible. Okay, I think you can learn this maybe next year because I think Yichen told us that we consider everyone sitting here know abstract algebra. But you know what I mean, right? And whatever. Okay. So we can consider this ring R as a R module R, right? We just think the group action is multiplication, right? And we can see that if we consider this R as R module R, then actually I also want to tell you something about what is quotient module. I think everyone here, if you start AA1, you learn quotient group and the quotient ring, right? Actually, we can also define a quotient module. We see that in a module R module M, we consider this M as an abelian group, which means that its addition is commutative. And if since M is a commutative ring, then all of its subgroup is normal, right? So actually, we just consider maybe if V is additive subgroup of M, where M is a group, right? Then V is here our V is commutative, right? And no, our V is normal, right? So we can do it as a quotient ring, quotient group way, which is M quotient V. And if M is an R module, we can see that this M quotient V is also an R module. I think I will write the technical definition here because I think we will use this later. Yeah. All right, our quotient module is defined that if B is a submodule of A, actually this is just the B is a subgroup of A if we just consider it as a group and we ignore the ring there. And then we can see that our quotient module contains all of these cosets, right? Contains all of this coset, and we will add some things. We can define addition and a scalar multiplication in this quotient group also, which is defined by A plus B plus B plus B is equals to A plus B plus B. And if we did a scalar to this, R times A plus B is defined as RA plus B. And I will not do checks the well-definedness of this here. And I think if you are interested, you can check this. Let's just leave this as a homework, as Keeson always do. Okay, then you guys remember we just defined a graded ring, right? We can also define such a thing called a graded module. Actually, it's also very similar. Let's consider M as sorry. Let's consider M as a R module. Then first, then we call this M a graded module if it satisfies first M is equals to direct sum of Mi, right? And the second thing will be that in our graded ring definition, here is SDSE belongs to SD plus E, right? And here it becomes RIMJ lives in Mi plus J. We just change this into a Ri because we know that if we just consider this M, if there is not a multiplicative in M, the scalar multiplicative is a group action between R and M, right? Yeah, and we can see that here those Mi are a subspace of M, and we call it the homogeneous pieces of M of degree R. Okay, let's just go back. This is our module thing, and now let's go back to what we are just talking about. Okay, we just talk about what is a graded ring, right? And also we define what is a graded idea. Here is a proposition that we talk about if S is a graded ring, and A is a graded idea of S, then our claim is that S quotient A will also be a graded ring. And it will equals to SD quotient A intersection SD. Yeah, actually, it's just a quotient each piece by piece, and we do direct sum to this quotient thing. And we will not go through the whole proof of this proposition, but we can have let's just can how see why this is right. Because we can see that this S quotient A, this thing, what does it contain? It contains coset of A, right? And this, or S in S, and you know, we can write this S as a sum of SD, because this is how we define direct sum, and also this A will equals to direct sum of SD intersection A, right? We just prove this the equivalence. And if we see this, then we can write this S plus A is equals to sigma SD and plus this, right? And I think if you need a more precise proof, I think you need to go to elements in S plus A, but we just consider this sum and this sum as a same kind of sum. Then you can just think this is SD plus A intersect SD, right? Sorry. This S is small s and this S is the big S. I think I just write them as the same thing. But we can see this, right? I need to say that again, this is not a very precise proof, but you can just see this is right. And so, and we can see this is a cos inside this sigma thing. This thing is a coset of A intersect SD. This thing lives in SD, and it is a coset, right? Coset of A intersect SD. And the whole proof also I will leave as a homework if you are interested. And I think in our maybe first or second lecture, we talk about what is coordinate ring, right? And can I ask another person to help us write the definition of coordinate ring? Maybe Lydia, do you want to try? Joshua, are you in that lecture? Okay, do anyone remember what is a coordinate ring? I think besides master students, I don't want a master student to answer this question.
Hey, by the way, so mostly, by the way, are you when are you teach all this algebraic geometry and abstract algebra second year or what?
We in our MAT course we teach abstract algebra in year 2 sem 1 and algebraic geometry course we offered in year 2 sem 2. Yeah.
Or is it not offered in our physics course?
Please answer this question. She just asked why we not offer this course in physics class, physics department.
What are the allowed handbook?
Algebra is not limited. Yeah.
Maybe you can ask it.
What?
Then maybe Rachel, can you help us write the definition of a coordinate ring in A? Yeah, we define if A in A and B algebraic set, then its coordinate ring is defined by Ka equal, sorry. It's defined by Ka equals to K adjoint x0 to, oh, I think at that word is just x1 to xn, quotient by IA, right? This is a definition of coordinate ring in AN. And actually, we can define a homogeneous coordinate ring in PN. Actually, this is very similar. We define if V is a projective variety in Pn, then we define its homogeneous coordinate ring. I just write coordinate ring, homogeneous, as K hom V equals to K adjoint x0 to xn, and it is quotient by B, where B is idea of V. And if you remember what we talked about the last class here, because this V is lives in Pn, right? So what is the difference between this idea and the previous idea? This idea is graded, right? Right? Okay. Yeah, because we just mentioned this K x0 to xn is a graded ring. So after it's quotient by this B, it's also a graded, right? We just talk about this a few minutes earlier. And that proof, I think, is just work for this to let you see that this quotient ring is also graded. And let's write this quotient. Sorry, okay. Let's just write this K homo B as a direct sum of all of its homogeneous part, right? And let's see what's next. And also, why we talk about those modules thing earlier, because I try to tell you that a ring R can be treated as a R module R, right? I think the slash should be here. See a R module R, right? Then what if we quotient this R by an idea? Also, in our last class in abstract algebra, we talk about what is a submodule of an R module R. Lydia. Then did anyone know? Try to think what is a R module, R submodule? It's just the idea, right? Okay, yeah. So we can consider an idea I as a submodule, R module I. So if these are quotient by I, then we can quotient I here also. And we can see by our previous talk about module, we can see this as a R module R quotient I, right? So let's go back to this thing. We see this thing as a quotient ring, a quotient ring, right? And if we treat it as a module, we can see that this is also a module, where its ring is it's a module over a polynomial ring, right? Can you see this? Okay, I will repeat what I'm trying to say. We can see if we do this quotient ring, quotient R by I, then we can treat it as a R module R over I. So by our definition, this K homo V is a quotient ring of quotient of x0 to xn and the quotient by an idea IV. And we can treat this as a module over this polynomial ring, right? Because you see this R is a module over R. This is the same R. So we can treat this R over R as a R module. Also here, we can treat this homogeneous coordinate ring as a module over K adjoint x0 to xn, right? And we define all these things because I want to introduce our main definition here, which is a Hilbert function. And also, we start from a projective variety in Pn. And we define its Hilbert function, HVM, to be the dimensional of its homogeneous coordinates ring and it's the dimension of the m grad of its homogeneous coordinate ring. This we defined by a function which call it as a Hilbert function. And the module is just we replace its scalar field into a ring, right? So we can repeat what you learned about the vector space thing in linear algebra into whole module thing. And we can see this dimensional is just, you can think it as a dimension of vector space. I think you learned this in linear algebra, right? And did anyone know what is this? By our, we know that this is the m grad of the coordinate homogeneous coordinate ring. And if you remember, this is just equals to the m grad of the ring quotient the m grad of the idea, right? So this is where equals to k x0 to xn. It's m grad and the quotient the m grad of b. We can see this, I think, previously. It's just, let me see. I think it's just this, right? It's just this, right? We can see that the d grad d piece of the quotient ring is just the d grad of the original ring quotient the d grad of the idea, right? So we can see this, and from this we can see that the dimensional of the homogeneous coordinate ring is just the dimensional of the m grad of the coordinate, the polynomial ring, and minus those dimensions that vanish in this projective variety, right? And I think later we can see some example of this. And first, let's do a very simple example of this Hilbert function. We just consider this V as the Pn, the whole space, and then we can see that its idea is what? What is the idea of a whole Pn? Huh? It's zero, right? It should be zero because we are trying to look at a function that equals to you bring into everything in Pn and it comes back to zero, right? So it should be just a zero, nothing else. And then if we do this quotient thing, a ring quotient by just a zero idea, what it gets, just this ring, right? So our homogeneous coordinate ring of Pn is just the whole polynomial ring, right? So now let's see it as a graded ring, and it's graded. We know that it should be the subspace that spanned by monomials, right? By monomials of the same degree, because I think this is just from our last section that is every grad is just a homogeneous polynomial with degree d, right? So we can see that if we just consider its first grad, and we can see that it contains what? It just contains maybe x0 is in it, and maybe x1 is in it. Also, maybe 2x2 is in it. So we can see that it is just, and also what? Maybe x0 plus x1 is in it because x0 plus x1 is also homogeneous, right? We just define it as the degree of this, the homogeneous polynomial in this ring. And we can see that if we see this thing, we can see that this is just spanned by this monomials, right? X0 to xn. So what is the dimension of this? I think it's n plus 1 because we started from x0, yeah. And so by our definition of Hilbert function, HPN 1 is just n plus 1, right? This is the definition. And also we can see that maybe if we consider as its next grade and its second grade, what it contains. I think it contains maybe something like x0, x1, or maybe x0, x1 plus x2 square, something like this, right? We can see that this is spanned by what? Spanned by monomials with total degree 2, right? Maybe something like x0, x1, or maybe xn to the square, something like this, right? So how many things can we get here? I don't think this is a very hard problem. I think you should add something more because we can use this, right? So I think should be n plus 1 choose 2 and also plus n plus 1, right? And you can compute this later. I don't think this is very hard. And actually, let's see what time it is. And actually, we just see its first and second grade, and we can find a generalized thing about this. What is the k gradient of this ring? It is spanned by what? Spanned by monomials with total degree d, right? And here, how many variables do we have? N plus 1, right? So if you want to count how many monomials with total degree d in here, what should you do? This is just, I think, a high school problem. Can anyone solve this? Yeah, this is just a high school problem. I think in high school, you just put whole this thing into n plus 1 box, and the box can be empty, right? This is the same, right? And so what is the answer to that? Does anyone remember this? I think also probability class involves this, right? Lydia? The question is, let's simplify this into a way that high school students can understand this. We have D box. We want to put it in n plus 1 box, and each box can be empty. So how many ways can you put this box? I have D box, n plus 1 box. Yeah. Can be empty, can be empty. Do you remember how to do this? Shachi, do you remember? I think Tilly told you. Huh? Box can be empty. Yeah. Yeah, box can be empty, and it should be different box, right? Because here our x0, x1, x2 are different variables, right? So we consider this box as different box. Huh? Yes, can. All right, if you forget how to solve this, go back and ask your high school teacher. And I will tell you that this answer should be n plus d choose d, right? This is the answer, right? If you forget, I think maybe we can discuss this in our maybe break time later. Choose n is same, right? N plus d choose d is just equals to n plus d choose n, right? This is just the same. Maybe you can give us another seminar later about this. Okay, and so we can conclude a conclusion that H, P, and M. Is this equals to? We just change these things into M, right? What is the answer? So it is m plus n choose n, or maybe you can write it as m plus n choose m. This is just equal. And what is this thing equals to? If we want to maybe, how to say this word? 展开来. Expand. What is this? Lydia, can you answer it now? Over m factorial and n factorial, right? And also we can write this it as m plus n times until m plus 1 and divided n factorized, right? We can see if we fix n now, we just consider Pn and maybe we consider this n to be 2, then we consider P2. Then what is this about m? This is a polynomial, right? This is a polynomial about m with degree of what? With degree of n, right? Can you see this, Lydia, now? Because here is n1, 1, 2, and there are n thing, and its highest degree is m times n times. So it is a polynomial with degree n. Okay. So we can see that this Hilbert function, if we just treat it as a function to m, this is just a polynomial with degree n. And we can put a motivation here. What is dimension of Pn? I won't go into details about what is dimension because I think Larry told us these things in lecture 3, right? So we just, it's called Pn. So I think it is easy to understand its dimension is n, right? We can see that this is just the degree of the polynomial. And should we talk about more things? Do you want to take a break? Okay, then maybe we can take a break. I think maybe from until maybe 8:30 or 8:35. Okay. Yeah, because this is just a seminar, not a lecture. I think you can maybe want to talk about some topic about this. Okay. Oh, it's a break. It's a break. You can talk, and maybe you can go to a fast. Go to WCL one. Don't be so quiet.
Why? Yeah, but I'll get extra credit there and we pay, right?
你现在有球的，ME 有的那个。
For now, I think that is for credits. If I take more than 12 credits, then I have to pay or what? It's not fair. This one is 5 credits. I want to do, obviously I want to do mathematical analysis, but I cannot do it because
你讲讲我像后面一个讲点什么，因为我想会举几个例子而已，然后我就会投出一个证明，因为你看到这个东西已经是个 polynomial 的。我想告诉你的是，当 m 足够大的时候，它并不是个 polynomial，然后我就要证这个，这是我后面1个小时做的事情。你看它这么长，就是因为这边我只是想介绍点模具的东西，这个我已经讲一下了，然后这块我也已经讲掉了，所以其实剩下来的东西，当然这个 proof 很 technical，我觉得1个小时内。
I feel I will say sorry to Lydia. In next hour, I will not kill you that much. I don't think there is any. Oh my! I'm roasted.
然后他打在底下，他在那里跳舞。对对对，他想看看，这个比别人就是为什么他这样退，因为人家太配。
6条都用完了。
要不然今天我要怎么分钟？买的比他更大。有啊，有类似。哦，他自己都说了吧？啊，对，特别是选手，他自己都说这个可以给他放拍到本人的选手。那我
Okay, I think we will come back. So in our last an hour, we define what is a Hilbert function, right? And in our later another hour, we will see some example about Hilbert function, and we can see that just now we see that the Hilbert function of Pn is a polynomial with degree n, right? And I can first claim that any varieties Hilbert function, if the dimension goes very large, it will become a polynomial, and we call this polynomial Hilbert polynomial. And later we will prove this theorem. But that's later thing. First, let's check some look at some examples of Hilbert function. Let's consider IV is idea x0. Sorry, there's no comma here. This idea in K adjoint x0, x1, x2. We can see this is an idea of a projective variety, right? Because we know that there is also Naus-Delis's theorem in projective variety, and it says that a projective variety will correspond to a radical idea, right? And of course, you can prove that this is a radical idea. Do you know how to prove? I think all of you know that. And since this is a radical idea of so it corresponds to a V, right? Which means that if we put a V here, it's just a V, right? And we can see that this variety actually is just x0 equals to 0, x0 equals to 0, or x1 equals to 0, put this together. But I don't think this is very important. And we can consider what is Hilbert function of this variety. And actually, we can see that first, here kv is equals to kx0, x1. What happened? X0, x1, x2 quotient by this idea, right? And we just say that if you want to compute the Hilbert polynomial of this, we can just compute the Hilbert polynomial of this, and we minus those dimensions that vanished in V, right? And we already know what is dimension of m grad of this polynomial ring. It should be m plus n choose n, right? In here, we discussed this in P2, so it should be m plus 2 choose 2, right? Which is just m plus 2, m plus 1 divided over 2, right? And first, we can see that in this idea, it is generated by x0 times x1. It's already with degree 2, right? So there is no degree 0 or degree 1 polynomial in this idea, right? So we can see that if we want to compute its Hilbert polynomial of hv0 and hv1, this two is just equals to hp20 and hp21, right? Because we did not minus any dimension here. No dimension is vanished here. So hv0 is just equals to hp20, which is 1. And here this is just equals to h. I understand the torsion now. P2, 1 is just equal to 3, right? Because it is 3 choose 2 is 3, right? And we can see that if we consider the idea second grade, we can see that this is spanned by what? Spanned by x0, x1, right? So if we quotient this idea, this one dimension just vanish, right? So if we want to calculate this is equals to hp22 minus 1, right? Because one dimension is vanished here. And what is hp22? It is 4 choose 2, right? Which is 6 minus 1 is equals to 5, right? And if we compute another, maybe in grade 3, x0, x1, 3, we can see what is the monomials or homogeneous polynomials with degree 3 in this idea. We can see that this is spanned by 3 things, right? We just, because x0, x1 is already have dimension 2, we can just add another dimension. And how to add this dimension, we have 3 choices, right? Times x0, times x1, and times x2. So this subspace should span by x0 square, x1, x0, x1 square, and x0, x1, x2, right? This is spanned by these 3 things. So we can see that the 3 dimension is vanished here. So if we want to compute this Hilbert polynomial, we just put the dimension of p to 3 grad and minus these 3 things, right? And so hv3 should equals to hp2 3 minus 3, right? And hp2 3 is what is this? 3 plus 2 is 5 choose think is this right? Yeah, it's just a 10 minus 3 is equals to 7. Did you find something? H0 is 1, H1 is 3, H2 is 5, and here 7. It's like a polynomial, right? It's just a polynomial. And actually, it is just a line. And if we can see a general case, we can compute the x0, x1 is m grad. And we can see how many things here. Because totally we want to put this thing into m degree with m, right? And we already have degree 2. So since it should stand by x0, x1 times something, right? Where here the something is monomial with total degree m minus 2, right? I think this is just another put ball into box thing. And the answer should be m minus 2 plus 3 minus 1 choose 3 minus 1, right? This is just m choose 2. If you don't know this, just talk after class. So the Hilbert polynomial here, it should be HP2m minus this m choose 2, right? And this is m plus 2 choose 2 minus m choose 2, right? And this equals to m plus 2, m plus 1 over 2 minus m minus 1 over 2. And if you compute this, you will find this is equals to 2m plus 1, which is right? Because if you bring into those things we just computed from 0 to 3, it is just 1, 3, 5, 7, right? So we can conclude that HBM is equals to 2m plus 1. And we see that this is a polynomial of m with degree 1. And if you can check that this is just the degree of this idea. I think how we define the idea is by its crew dimension, the crew. Oh, no, I mean, the degree of this variety is equal to its crew dimension of its coordinate ring, right? I think Larry told this before. And I will not repeat this thing here. And I will give 2 more examples, but I think I just skip proof. Although I think Keaton is very interested in this, but I will not do it here because I haven't computed this already. Sorry. First, let's consider X is a project variety in P2 that it contains 3 points. And we want to compute this things Hilbert function. And I think if you want to compute this, you should write its idea and we compute this. To compute this, right? But actually, I haven't finished compute of this thing yet. But I will tell you that the solution should be hx1 is equals to, there are 2 cases, 2 or 3. 2 if these 3 points are collinear and 3 is otherwise. And hxm is equals to 3 where m greater than 2. And first, I will say that you can see here it becomes 3, which is a constant. We can treat constant as a polynomial with degree 0, right? And you can see that 3 points in P2, since they are distinct points, the dimension of this variety is also 0. So you can see from the last 3 examples, there is a correspondence. You see the dimension of the variety is just equal to the degree of its Hilbert function, Hilbert polynomial, because eventually it becomes a polynomial, right? We should we should don't see this, just see this, because we see that when m is large enough, it becomes a polynomial. And when I read this, I think a question is that the solution says it equals to 2 when 3 points are collinear, and equals to 3 if they are not collinear. And I think the question is, how do you understand this collinear thing in a projective space? Because if we see that in just, if we think it in R2, if we see 3 points is collinear, it's just they live in the same line. But we can see that if we want to think P2, we need to put it into 3 dimension, right? Because we know that P2's element is actually those lines across origin in R3. We just consider RP2, like, because I cannot draw CP2, right? So how do you mean if you say that these 3 elements are collinear? Actually, how do we think about those lines? We use its homogeneous coordinates, right? And if we, it's just those 冒号英文怎么说？column. Okay, we just use this column thing. I think Adrian and Risha introduced this. And this is just equals, we can choose any points in those lines, right? So if you want to see a collinear here, you can see if we select these 3 points to be at a line, you can see actually these 3 lines and those and this line, it becomes a plane, right? You can only achieve this when this, it means you can only achieve these 3 points at a line when these 3 lines lives in the same plane, right? So actually, this collinear here, if you need to explain this in R3, actually this is a coplane, I think. They are lives in the same plane. I just talk what is collinear, but I don't think this is very related to today's topic. But if you want to compute the Hilbert function of these 3 points, you need to consider whether these 3 points are collinear. Yeah. And also there is a theorem says if X is a point in, sorry. If X is a point in Pn and it consists of, it is a set of distinct points, is a set of S distinct points, then Hx R will equals to S, or I think we use M in this lecture, right? Will equals to S when this M is greater than S minus 1. This theorem I will not give a proof because I did not prove it yet. But you can see that since they are distinct points, and again, the dimension should be 0, right? And also we can see it becomes a constant which has degree 0, right? And from all this thing, we can see that in our first example, Pn, and in our second example, ID, where V is idea generated by x0 times x1. In these 2 cases, it is just a polynomial. And in our latter case, this distinct point case, becomes a polynomial after a number, right? So actually, this can motivate us to have a claim. Actually, this is a theorem, and I think sometimes some book tells this as Hilbert theorem. And also, I find some other books called Hilbert theorem is other things just related to this, but I'm not very sure. So I think you can call this here, and it says that if V is a projective variety in Pn, and there is a unique polynomial PVT lives in Qt. Actually, I think Qt is just ZT, right? Oh no, not really. I think also can write V here. I'm not very sure about this. Such that PVM will equal to HVM. This HVM is just the Hilbert function we just talked about, and this PVM is a polynomial in QM. And this will equal for all sufficiently large M. Actually, I did not know how to consider this sufficiently large M here, but you just can understand if the M goes to very big numbers, eventually this function will become a polynomial. And moreover, I told you something about its dimension, its degree of this polynomial will equal to the dimension of the variety, right? Actually, this PV M will equal to delta over d factorized t to the power of d plus some lower term. And we can see that here this d is just the dimension of v. And the delta here is called the degree of projective variety, but I do not really quite understand what is definition of this degree. So we will not talk about this in this lecture. And later we will prove this theory, and we will only prove the first part, which says that there is a unique polynomial that equals to the Hilbert function, but we will skip the proof of this. Maybe we can read it later, right? And for this first part, I think let's go to some proof of this. Actually, we talked about this Hilbert function in projective variety, right? But actually, we can have a generalized form. We can just look over from this projective variety things and look into every graded module whose coefficient is a polynomial ring. What does this mean? The general version of this is suppose that R is a polynomial ring of kx0 to xn. And here K is a field, and we can, and also M is a finitely generated graded module. So this is why we talk about the graded module earlier, right? Because we want to use here. And we can see if M is a graded module over R, which is a polynomial ring over a field. And we can define a function h from n to n, which send each n to the dimension of mn. We see we already say that this m is graded, right? So we can consider its graded top piece. This is called Hilbert function of m. And we write it as hm m. We find that this notation is a little bit different with what we talk about in here projective variety, because in projective variety, this VM is actually, if we use the notation here, is H should be H K homo VM, right? But we just think this is a notation thing. I don't think we should this is just a notation thing, because we know that V and this homogeneous coordinate range should be correspondent, right? We call this thing as the Hilbert function of M. And if this M goes to large, for sufficient large M, or here N, it should be a polynomial in Qt also. And we call this Hilbert polynomial. And we can see that if we can prove this general version, then here M is a gradient module, right? We say that we talked about this earlier, that we can treat this as a gradient module over the polynomial ring, right? We talked about this earlier. So if we can prove its generalized version, we just bring into this module in, and we will conclude the conclusion in projective variety. And so let's prove this general version. Yeah. Okay. First, let's start from consider M is a finitely generated graded module over polynomial ring S equals to K. I think the proof use cosine here. I just use cosine. I think you can change it into S X over a cosine N to cosine M. And I will say that the whole proof used mathematical induction, and we will start induct from n equals to -1. Why -1? Because even we start from n equals to 0, it should be S equals to K cosine 0. It's also a polynomial ring. And if we think the more easier case, it is just we choose n equals to -1, then S is just equals to K, right? Okay, and we see since M is a gradient module, we can write it as a direct sum of MM. Then by the definition of gradient module that we talked earlier, if there is a X belongs to MR and there is a F belongs to SL, it will implies that Fx lives in MR plus L, right? This is just the definition of module, gradient modules. And we can see that each actually we can see each identity subgroup and we can consider it as a K vector space. Why I say this? Because first K is a field, so a K module is just a vector space, right? And you can check all of those vector space axioms, those 10 things, and you will find that this MM will satisfy all of them. So it is a subject space of over K, but only over K, not over the whole polynomial ring, because we see that if it multiply a cosine n, it will lives in MM plus 1, right? Not just MM. Because this cosine n is lives in S1, right? So it should, so the multiplication of those things should lives in M plus 1, not just M, right? So it is not closed after scale multiplication. So we can see this is not a submodule. It is just a subspace over K, not a submodule over the whole polynomial ring. And let's, by definition, this Hilbert polynomial function HMM will equals to dimension of MM, right? And we want to show that there is a PMM lives in QM such that PMM equals to HMM for sufficiently large M. And here we see that in our theorem, we say that unique, but of course, this should be unique, right? Because those two polynomials should be equal to this Hilbert function when M is sufficiently large. It means that from a fixed N and every point after M, these two polynomials should be equal. Then those two polynomials should just equal, right? Because there are infinity points after that point. And we will use mathematical induction to prove this. And I just mentioned that our base case, we start from n equals to -1. Here, the polynomial ring S is become just k, right? Because if n equals to 0, we adjoin to one thing. Then when n equals to -1, we just adjoin to 0 thing, which is just k, right? And in this case, we can see that our m is become just m0. Because how do we treat this s equals to k into a graded view? Actually, this is just x0 equals to k, and s1 equals to s2 equals to blah, blah, blah is just a 0, right? Because we did not adjoin anything. We cannot find a polynomial with degree 1. So all of this graded after except 0 should be not empty, just contain 0, right? And if we see this, then if we multiply this S1 thing into something in M, it just becomes 0, right? So our M1 also equals to M2 also equals to those things equals to 0. So we can see that our SM is equals to just K when M is equals to 0, and it is a 0 vector space when M is greater or than or equals to 1. So what is a Hilbert polynomial function of this? We can see that HM0 is just the dimension of K, right? And when M is larger or equal to 1, it should be 0, right? Because we see 0 space, this is just dimension 0, right? You have only 0. We see that this is just satisfying the theorem because we see that this here, M sufficiently large means M larger than 0. And 0 is just a 0 polynomial in the Qt, right? And this is the base step. We find that this is very basic. But then let's go through the induction step. And in this whole induction step, let's consider a map. This map, we called it as Xi n. We see Xi n is just a variable we adjoined, but we consider this map, also consider this as a map that from M to M, we sent each f in M to f times Xi n. Then we can see that Xi n times mm will lives in mm plus 1, right? Because Xi n is lives in S1. And we consider this map has a kernel. We call it K. And consider its co-kernel. What is a co-kernel? I don't think we learned this before, but it is just your codomain. Sorry. It's just your codomain. Why I write this? Your codomain quotient by your quotient by your image. What is image here? It is Xi n times m, right? So we call this thing co-kernel. And here we can see, actually we can prove that here the kernel is also graded. This k we are equals to km, where this km is equals to mm intersect k. And I will not go to the proof of this. I think leave as homework. But actually, I searched for some information that if we do a homomorphism to a module to another module, if this module is graded, and when we do this homomorphism to another module, when we do these things, we keep this graded, then this map's kernel should also be graded. And this homomorphism, we call this kind of homomorphism as graded homomorphism. Yeah. And also we can see that this C is also graded, right? We can see this by we quotient a graded module by a graded submodule, right? Because Xi n times m is also graded because everything in M, if it lives in MD, when we times cosine n, it will go into M plus 1, right? So we keep this graded structure here. So we can see that cosine nm is also graded, so this quotient should also be graded. And to prove this thing, we need to introduce a thing called exact sequence. I don't know, do you master students hear this word? Exact sequence, yeah. Actually, let me write write this exact sequence as 0 to km to mm. Here is cosine n to mm plus 1 and 2. Here is a canonic map to cm plus 1 and eventually to 0. What is this chain means? Actually, this thing we call exact sequence. It means that the kernel of the right map is equal to the image of the left map. Do you guys understand what I'm saying? We see that in this chain, every arrow here is a map, right? We can see that if we want to send 0 to km, we just send it to 0 if we want it become a homomorphism. And we see that km is a subset of mm, right? So we can just send everything in itself to itself. It's also a map, right? And how do we send mm to mm plus 1? It's by cosine n we just defined, right? We times everything with cosine m. And also, how do we send mm plus 1 to cm plus 1? We see that how do we define this cm? Oh, I forgot to write this cm is equal to mm quotient cosine and m minus 1. We can see that this is a quotient. If we forget its module structure, this is just a quotient group, right? And how do we define a map from a group to its quotient group? Just the canonic map. We set every element to its coset, right? And eventually we send everything in here to 0. And how do we see this is an exact sequence? Let me explain this. We just say that exact sequence is, it means that right maps kernel is image of left map. So we see that we see it from right to left. We see that this maps what is its kernel. Kernel is those things that send to identity, right? So we send everything to 0. So its kernel is just the whole cm plus 1, right? And then this map's kernel is cm plus 1. Then let's look at this m. Look at this m. We know that the canonic map from a group to its quotient group, it should be surjective, right? So the image is also the whole cm plus 1. So with that, this map's kernel is this map's image. And also, what is the kernel of the canonic map? Is the thing that you quotient by, right? Especially in here, in this case, it is cosine n times m minus 1, right? This is the kernel of this pi map. And we see that this is just this map's image because this maps times everything with cosine n. So its image should be those things in mm that times cosine n, right? It lives in mm plus 1. Is this map's image. And also, what is this map's kernel? It is km, right? Because we define k as the kernel of cosine n. And we just show that this should be a graded ring. There is a graded structure here. So specifically for this mm, if we do this cosine n, its kernel should be km, right? And then we find that how do we define this map? This map is just to send everything in km to itself. So this map's image is just Km. It's also satisfying that this image is equal to this kernel. And finally, how do we define this Km to MM? We define that we send everything to itself. So what thing do we send to 0? Only 0, right? We can see that this is also the image of this. So this is what exact sequence means. Do you guys understand? All right, I'll continue. And also that we can see that we already show that K and the C are graded, right? And what is so special about these two graded, graded module? We can see what if we times cosine n here. What is cosine nk and cosine nc? We can find that it is very amazing that these two things is all equals to just 0. Why? Because we define k as the kernel of the map cosine n. And the cosine n is sent every f to cosine nf, right? So if we, so what is its curve? Its curve is those things that send to, that times cosine n, it becomes 0, right? So if we act this cosine n on k, it should be just 0, right? And also why cosine nc is equals to 0? This is because that what is c? We define c as, wait. We define this c as m quotient cosine nm, right? So if we put everything in m, if we act anything in c, let me think. Oh, in c, its element should be element c in m, and it should be its coset, right? Plus cosine nm. If we add cosine n on it, then it should be cosine n times these things. By definition of our quotient module, this is equals to cosine nc plus cosine nm. And we can see that this is just cosine nm, right? Because cosine nc lives in cosine nm. This is called TFA statements in abstract algebra 1. And so we can see that if we act cosine n on everything in C, it should be just 0. So we see that cosine nk equals to cosine nc equals to 0. So if we act, so cosine n is just act like 0 on these two modules, right? So we can just ignore this cosine n. So we consider this k and c as what? As a module over k adjoint cosine 0 to cosine n minus 1. We can see this, right? Because originally it is a module over k adjoint n plus 1 variables. Now we can see that there is one variable act on those two modules just at 0. So we can ignore this variable. So it is a module over this n k adjoint this n variable, right? And if you know what is a mathematical induction, I think everyone here knows. By induction hypothesis, we do induction on n, right? Here it becomes n minus 1. So we can use induction hypothesis, right? So we can see that since this k and c is a module over just the k cosine 0 to cosine n minus 1, we can, by induction hypothesis, the statement is true, right? Which means there is a unique polynomial PCM equals to HCM, and a unique polynomial PKM equals to HKM, such that these two things are equal for sufficiently large m. And we will use this later. And let's compute a thing. Actually, I will say that our final goal is to show that you will see HM m plus 1 minus HM m will equals to PCM plus 1 minus PKM. This is our goal, and why we set this as our goal. We can see what is the right side of this equation. We see that it is a polynomial minus another polynomial. And both this polynomial lives in what? QM. So what is the minus of these two things? Another polynomial, right? And this polynomial lives in what? QM. And you can see that actually this two is just the m term of the Hilbert function of H and the m plus 1 term of the Hilbert function M. Also, I want to say that Hilbert function only defines on n, right? Because the dimension, the gradient can only be integer. So I think I know in China's high school math course, it will involve the sequencing because we can treat the Hilbert function actually just as sequence because it defines on n, right? And you can see if a sequence is the later term minus the former term equals to a polynomial, then what is the whole sequence be? A polynomial, right? I will give an example, like if maybe an minus 1 equals to n squared, and a1 is equals to 1 maybe. Then we can see this an is equals to maybe 1 plus 2 squared plus 3 squared plus 2 n squared, right? You see each difference is a polynomial, then the whole thing is also a polynomial, right? We know the answer is n times n plus 1 times 2n plus 1 over 6. I think this is another polynomial. So if we show this, then we can conclude that this HMM is a polynomial. And how should we see this? I think we can finish this in 5 minutes. If we want to show this, we can change this into show HM m plus 1 minus HCM plus 1 equals to HM m minus HKM, right? We can show this, right? And do you remember what you learned, I think, how to say, rank theorem in linear algebra 1, I think. It is said that rank plus nullity is equal to dimension of domain, right? This is for matrix, and if we consider it as a linear transformation, it is the dimension of kernel plus the dimension of image should equal to the dimension of domain, right? And we can just use this. We see that here the left side HM m plus 1 minus HCM m plus 1. This is equal to the dimension of m plus 1 minus the dimension of cm plus 1, right? And this thing is equal to what? This will, because we know that this cm plus 1 is m plus 1 quotient cosine n right? So this thing, if we consider the canonic map from m plus 1 to cm plus 1, here we can see that its kernel is this cosine n and we know that canonic map is surjective, right? So the image is just the cm plus 1. So by this equation, we can see that this is just the dimension of domain minus the dimension of image, which is the dimension of curve, right? Kernel, right? So this is equals to dimension of cosine n And we can see from the exact chain that what is this kernel? This map's kernel should equal to this map's image, right? So it is just equal to the image of cosine n. And also, let's see the right side of this map. It says that HKM. Oh, we want to compute HMM minus HKM. It is equal to the dimension of MM minus the dimension of KM, right? And we back to this exact chain, which is the first few terms of the exact chain is 0 to Km to MM to MM plus 1, right? I will draw a picture. First, we send this Km to also Km, which lives in the whole MM. And if we times cosine n, we define this k to be the kernel of the cosine n, right? So this km will become 0 here. And so the whole mm should live in cosine n mm, right? And the codomain is m plus 1. So we see that if we consider this map here, we see that its dimension of kernel is dimension of km plus its image, which is, we just write it as dimension of im cosine n. It will equal to what? Equals to dimension of domain, right? Which is dimension of mm. So we can see that this dimension of mm minus this dimension of km will equals to dimension of image cosine n. So we can see this is just HMM minus HKM is equals to dimension of image cosine n, right? And we already show that this dimension of image cosine n is equals to HM plus M plus 1 minus HC M plus 1. I don't think we can actually write this. If we change this thing, change the order of this, we can conclude that HM M plus 1 minus HM will equal to HCM plus 1 minus HKM. And we know that for sufficiently large m, this will equal to PCM plus 1. This will equal to PKM, right? Why do we need this sufficiently large condition here? Because we see that in our base step, there is one term that is not a polynomial, which is the first term, right? We see here HM0 is equal to dimension of k, which is not 0, right? This is not a whole polynomial, but it's a polynomial without the first term. And so if we do this induction, we can see that it is the difference of two terms be a polynomial, right? So for the first term is not polynomial, and if we do induction on this, it will be more and more terms that is not satisfying this polynomial, right? So this is why we need this sufficiently large m condition. So we have proved that for a graded module, the Hilbert theorem is right. And we already see that projective varieties coordinate ring is a graded module. So we conclude the Hilbert theorem in the projective variety version, right? So we prove this. And I think that will be everything I prepared today. And I'm thankful for everyone to hear until now. And because of this is our last seminar in this short semester, maybe in the end, let's invite Yichen to do some introduction to his next plan. Yeah.
Okay. All right. I think it's close to the end now. I have some good news to share. But first of all, let us give a hand of applause to the committee first for organizing this seminar and the good effort put by the speakers to the preparing the lecture notes. But I think you can see that I think we're quite new to this kind of event. So there are a lot of improvement to do in future. I think I can challenge these speakers. Go back and watch all your own recording, see if you can learn anything from your own presentation or not. Okay, so I think this is a very way to like check whether you did a good job or not. The other thing is partly why we have this seminar is because we're gonna start a new course here in XMUN. The new course is about algebraic geometry. So yeah. So actually, this is kind of preparing them for this new course to come in the April SEM. It's a new ME. So this ME will be open for year 2, SEM 2 onward. Okay, so you can come and audit. Yeah, you can come and audit because there's a prerequisite to this course that you need to do after Algebra 1 first, unless you did it. Yeah, if you did it, then maybe you can take it. Yeah, otherwise you can come and audit the course. It's not fun. Okay, you like to do assignment? Okay. Sure. Yeah. So if you want to know more, please come to the ME meeting. Is the ME meeting scheduled out yet? Not yet. Okay. Maybe Peter will schedule a ME meeting soon. Hopefully, I think it's after the exam week of short SEM, I guess. And that another thing is we're gonna have a quantum mechanics seminar next semester for 2 months at least. Maybe one on quantum mechanics, the other one on quantum field theory, because I hired a research intern from USM. Okay, so yeah. Yeah. You know him?
I actually don't know much about him.
Okay.
Except I'm one of the members
of
the chapter of Malaysian Quantum Initiative.
I see. Maybe you know him. Yeah, so I guess he will come and answer or teach me at least on quantum mechanics and learn a bit of quantum field theory, maths related to quantum field theory, hopefully gauge theory or something like that. Because why I have this motivation, because my maths area is closely related to QFT. Yeah, hopefully can learn something from him. And we aim to produce an article, at least kind of expository article, because we actually already started on it on quantum mechanics, because the last short SEM we did it, right? You come here, right? We did it last short SEM with Physics Society, and then this, I think you come once, right? I saw you once. Yeah. So we are halfway finishing it. So we try to make it as mathematics rigor as possible, because if I'm gonna go and read the physics book, I don't understand those experiments. So I need a physics guy to explain to me.
So actually, there is a quantum hackathon in Southeast Asia.
Okay.
So I was the one entering for the quantum hackathon, and if anyone around here is interested, you can join me.
Okay.
I'm very lonely.
Okay. Okay. Yeah. So right. So if you're interested, you can contact me. So we're also glad that there's 3 staff here tonight, because I think they came almost to all the seminar. Right? So we hope that our student can closely work with them closely. Hopefully, yeah. Yeah, maybe you can talk to them, ask them what they do in their research. Then maybe you can do a FYP with them in the future. Yeah. Okay. I think they are very friendly, very nice. Our new blood in the MAT department. Yeah. Please get to know them more. Yeah, maybe get them to talk here more. Okay. I think that's all. So if you want to know more about the upcoming seminar, I think you can contact me. I think I will see how to arrange it. And then we have new course next semester. And next semester, GE, I thought I will be teaching general topology and algebraic geometry. So ME. So for all of these are open for year 2 Sem 2. Okay, so if you are interested, you can look for me. Okay, I think that's all. Pass back to the organizer.
Okay. So that one. Yeah, so thank you all for attending all these 5 seminars. I will try to continue to host these kind of seminars in the future. Yeah, so that these students can interact more and so on. So I don't know if our multimedia team can take a last picture. Okay, so we'll just take a simple picture with everyone here, and then yeah, can say yeah, have a nice holiday next week.
What?
Yeah. Okay.
Just look up on final exam.
Done. So,
Guys, I have one update. And then I recently started a company called Meet, and it's a social gaming platform for the gaming community. And currently I don't think we have enough programmers. So please, anyone interested, please just contact me.
Why you?
Wait. I mean, I didn't mean to come here to. I didn't come here. Let me come here, but I wanted to. But I wanted to But I want to like introduce my startup, which was founded, which was actually founded by me and the 5 members of the whole team of my entrepreneurship and sustainable development team. And
I think, yeah, you said how long is it going to take for you?
just for a while, I'll skip the annoying parts.
And for now, everyone sit into the middle so that we can have a nice picture.
I mean for. Can you off the mic?
Let us take a picture first and then,
Oh.
yeah. If you want to promote, have you promote your student council?
I beg you, please.
One, sit and then sit in the middle, all right? Right, nice and cozy.
What's this thing over there? It's my shoes.
Okay. Okay, post still okay.
See here.
Trees.
One, two, three. Alright. One, two, three. Okay.
Very professional. So this is a portrait shot. Okay.
One, one, two, three. One, two, three. Okay. Also, we're taking a video, so Risha say 1, 2, 3, then you guys say it's alright. Okay, thank you.
So, okay, right, we're doing now, right, so it's 1, 2, 3, it's a wrap, okay, right, so I will start now, okay? Right, natural number starts 1, so 1. Controversial. 1, okay, 1, 2, 3, right, it's a wrap, wait. I was practicing. 1, 2, 3, you also say together, alright, so I start, alright, 1, 2, 3, right, it's okay.
One more time.
Right, yeah, alright, 0, 1, 2, alright, it's okay. You will see the video on our IG then. Okay, so thank you all again. We will have more events like this in the future, right? Bye bye. Yeah, we will do it on our team. Thank you. Sorry.